Final section of the semester, we're going to be looking at another type of, it's not online yet, correct. There's a couple things I need to put in the online one that I'm going to draw in today, and then I'll get it online later. Okay. So we're looking at, this is the example I'm using here is the Hamilton Standard 14RF-9 propeller, which is mounted to a Pratt & Whitney Canada PW-118. This is a free power turbine. And again, I'm not looking at the specific engine propeller combo, right? There's all kinds of engines and propellers out there. But what we're looking at is this has a control system that's unique from the others that we've done. And specifically, it has a threaded, what's called transfer tube now, where before we talked about a beta tube that was on the TPE 331 engine. So that controlled and provided blade angle feedback in beta. This one, and it used a sleeve. This one is threaded, so it threads in and out. And we'll look at how that works in a minute. And it's called a transfer tube because it actually works for both beta, alpha, and beta modes. And so we go away from the, it has to move, it's still moving and it's still doing its actuation, whether you're in alpha or beta mode, whereas the beta tube that was on the TPE 331 with the sleeve, when you got into alpha mode, it essentially locked that out. It became an open port between the propeller and the engine for oil. And in this case, we're still going to use that tube and its actuation to control the propeller blade angle, but what is actually controlling the position of that tube is going to change between alpha mode and beta mode. And so we'll look at that. So just some general information on the propeller. 14RF-9, so 14RF, it's the major model type. That's where the 14 comes from. It's a Model 1 in Hamilton Standards book. And screen. So the 14RF-9, what it's talking about, major model type, they call it their 1 series of propeller. It's a 4-bladed version. They do make other versions of this propeller, 3-blade, which would be an RF-13, sorry, a 13RF. And I think they make a 5-blade as well. But they're on actual different type certificates. Sometimes you have propellers where different numbers of blades are on the same type certificate. In this case, they issue different type certificates based on number of blades. Blade shank size is an R. That'll come into play in just a minute when we look at our blades right here. That's with the RFC 11U1-6A. That's the blades, by the way. F is the flange mounting. That it's a flange mount. The 9 is the specific model designation. So you can have several different 14RFs, but part of the -9 includes those blades, the RFC 11U1, as well as the RFC 11E1 and a couple others. But it's the blade designation that in this case is going to fit on the Embraer 120 turboprop. But again, it doesn't matter the airplane it's on. I'm not really concerned about the engine and knowing the propeller so much as just understanding it's a different mechanism and how the mechanism works. And then there can be special notes there for other things. The blade then is the rest of it. So you can see the shank size is an R. It matches up with the hub. These are fiberglass blades with an aluminum hub. The C is the blade shape. That's just their code. 11 is the propeller diameter. It's not the individual blade length. It's not a 22+ foot diameter propeller. It's a 11 overall foot diameter propeller. Kind of. We'll get to that in a second. Full feathering, reversing, 2-section de-ice boot. And then right-hand rotation is the 1 there. And then the -6, this is the interesting part. The -6 there means that's actually a reduction in propeller diameter 6 inches. So they took one of their propeller blade standards and they're reducing the overall propeller size by 6 inches, which means they're shortening the blades by 3 inches each. And so the actual prop diameter ends up being 10 feet 6 inches. Okay, plus or minus, there's some tolerance in there. And then the last part, A, the blade spinner interface type. That's just how the spinner hooks on, how it interfaces with the cuffs of the blades and all that. So nothing too important there. But the interesting part is where they do the shortening thing. You know, they take the same blade, basically the same airfoil shape, and they say, we need to make it a little bit smaller so it'll fit on this airplane, and you know, the blade tips won't hit the ground or hit the side of the fuselage. So here's what it looks like in real life. Here's one installed. You know, this is that Embraer 120 I was talking about. Close up of it, you can see it sitting and feathered right now because it's a free power turboprop and shut down. Kind of rounded tips. It's got nickel on the leading edges, the de-ice boot. These little yellow lines are feathering lines to verify that it's fully feathered, and that we'll see in just a second. One of the points, you know, I didn't say up here, we'll get to it here. But the engine, Pratt Whitney 118, this is kind of an interesting one. It's a 3-spool free power turbine. So the core of the engine, the gas generator, actually has a low pressure spool, a high pressure spool, a low pressure spool, so a low pressure compressor and a low pressure turbine, a high pressure compressor, high pressure turbine that are separate, and then there's a third turbine which drives the prop gearbox and the propeller. So they call it a 3-spool engine. And you can see the various RPMs those run at, 1900 shaft horsepower or so, and about 1300 RPM at the prop and gearbox, where the different spools are spinning at 33,000, 27,000 RPM. Again, 4-blade, aluminum hub. Now, here's the big thing. This is different than almost all the others we're seeing. What do we see there? We see oil dual acting. So this propeller actually does not have any springs or counterweights on it. We use oil to go to high pitch, and we use oil to go to low pitch. And so there is a bit of centrifugal force, you know, on the blades. Which way do the blades want to go naturally due to centrifugal force on them? What do they want to go to if they don't have counterweights on them? Parallel to the plane of rotation. They're going to want to go to a low pitch. But that is a very minimal amount of force on these blades. Okay, so the majority of how these move is oil. Okay, so they have to use oil to go to feather, they have to use oil to change, to go through their pitch range, and they got to use oil to go to fine pitch, and they use oil to go into reverse, just acting on opposite sides of the cylinder. Okay, we've seen the piston inside the dome. Often, you know, all the other props we've looked at, oil pushes it one way, springs or centrifugal force pushes it the other way. This one has 2 oil chambers, one on the front and one on the back of that piston. Flange mounted, and then this also, the other big key point that I want to show you today is that it has an internal threaded beta tube for blade angle feed. It's for blade angle feedback. It's also how the oil gets to the various chambers to go to high or low pitch inside the propeller. And the reason you start to see these is because we get into integral prop control units, okay? And even newer ones, now this one isn't, but a newer one gets into a full digital prop control unit. This one still has some hydromechanical components in it. But what this allows is with this type of a beta tube arrangement, we can get rid of those, the flyweights, the hydromechanical. Now this one doesn't, this one still uses those. But the big brother to this, the Saab 2000, for instance, which is a newer kind of turboprop, but with a similar prop, similar engine, that uses a fully electric, full authority digital electronic control for the engine and the propeller. So with this same kind of a threaded beta tube setup. So in the control schematic for something like this, the other thing this does is it allows us to go from where our previous free power turbine engine had 3 levers. Remember, we had a power lever, a condition lever, and a prop lever, right? Well, this is a 2-lever configuration. So it's a free power turbine, but it only has 2 levers. Okay? Whereas before we had the fixed shaft turbine, turboprop, that was a 2-lever. It had the power and the condition lever. And then we had our free power turbine in the PT6, the older one, that used the external feedback system with the beta rings and all that. That used 3, power, condition, and prop. This is a free power turbine, but with only two levers, a power and a condition lever. And you can see those are hooked up here. So the condition lever goes here, It connects to a feathering valve. The condition lever also connects to the speed governor. This is your hydromechanical governor, prop governor. And then we've got a power lever that goes to the reversing valve and the beta valve. Okay. It's not shown here, but it's also going to hook up to the fuel control on the engine. It's going to control the amount of power that the gas generator is putting out, but we're not looking at that directly in here. So inside this propeller control unit, power control unit as well. That's because on aircraft with hydraulic flight controls, the hydraulic things that move the flight controls are called power control units. So if you hear me swapping between them, I'm sorry, I teach both classes. But the propeller control unit, in this case, this PCU, has several items inside of it that often were separate before. So we've got the speed governor, which is essentially the propeller governor. Okay, we have what's called a least selector valve, and then that's tied externally to the overspeed governor. So we've talked about overspeed governors before. We have a reversing valve down here, right? And then we've got the feathering valve and the feathering solenoid. We've actually got two. So here's our mechanical feathering valve here and our feathering solenoid here. And you can see all these devices I'm talking about, for the most part, are hooked up to something called control pressure, which is the black with the two white lines. There's also supply pressure, the kind of dotted lines, and we'll talk about what those do in a minute. And then we have the pitch change screw down here at the bottom, and that's getting into where I said, this is a threaded beta tube. It's threaded in this pitch change piston. It's also threaded in the propeller hub over here at the left. And in the propeller servo mechanism at the left, the propeller itself, we have our piston, and the piston is right in this area right here. Okay. Kind of the gray, the dark gray is our piston. And that's connected to the base of the blades. They're keyed together to rotate the blades. And then we have, on that, there's two chambers. In front of it is our pitch increase chamber. Behind it is our pitch decrease chamber. And so that's where we get our dual actuation. We use oil to go to high pitch and low pitch. Connecting the PCU, the propeller control unit, which is on the back of the gearbox, and the propeller servo mechanism, essentially the prop hub, is our oil transfer tube. And it's kind of shown cut here. It's a somewhat long tube. And then external, I mentioned there's an external overspeed governor. So when we look at where these live on the engine, the main one that we're going to talk about, the propeller pitch control unit, this is on the back of the prop gearbox, directly in line with the center of the hub. And you can see the dashed lines there are that oil transfer tube going between the two of them. Okay. Then also on here is our overspeed governor, which is external. There's a mechanical pump. If I go back a slide, you have mechanical oil pump here. Now that's not the engine oil pump. The engine oil pump probably runs at about 70 PSI. This mechanical pump is running about 670 PSI. Okay, it's over 600 PSI. It's a very high pressure pump, but it's very low flow. There's also an electric auxiliary pump up there, which I don't remember. Oh, yep, there's the auxiliary pump here. And the reason we need that is because we use oil to go to both high and low pitch. We need that auxiliary pump to be able to move. We use that auxiliary pump for several different things, including auto feathering, electric feathering, testing. We can do a pump test. We can actually run it on the ground and move our blades both directions. And then there's also the fire extinguishing system handle. Why would the fire extinguishing system handle be hooked up to that? What do you want your engine to do when you pull or activate the fire extinguishing system? You want it to shut down, and particularly in flight, you want it to do what? You don't want to get fuel, but this isn't anything to do with fuel. It's going to turn that pump on. It's going to feather. We want our engine to shut down and feather if there's a fire. And so that's why it's connected to the fire system. Kind of interesting, because there isn't, remember, we don't have those flyweights that can automatically move the blades to the feather position. So we have to have some kind of a system to do that. So the propeller control unit, the main thing we're going to talk about, mounted on the rear of the gearbox, is connected through the transfer tube. It's operated directly by the power lever. And it's going to direct oil to and from the propeller in all ranges of operation. So alpha and beta and reverse, which reverse is part of the beta range. And that's going to control the blade angle in all ranges of operation. Anywhere from fine pitch to coarse pitch to feather to reverse. Okay, actually it goes reverse, fine, coarse, and then feather. So when it's hooked up, it looks like this. This is what I was talking about. We have our power lever going to the PCU. We also have the condition lever going to the PCU. Okay. So that's the full pitch control unit that controls those other items inside of it. So how does this thing work? What does it do? So essentially what we have is oil pressure from the propeller oil pump, one of the two oil pumps while we're running. Normally it's the mechanical prop gearbox pump that's run by the prop gearbox. There's the auxiliary electric pump for ground operation when the engine's shut down, as well as for emergencies and other things like that. And the oil pressure from those pumps comes in at the top here, and it's divided roughly into two paths. So one path is, and they're shown over here. So one path is the supply pressure in the dotted area. So you can see it comes in and it provides supply pressure, and supply pressure has the ability to basically bypass everything, and it comes down to our pitch control piston mechanism here. And this piston mechanism can move left and right. And so the way it does that is it pushes on a little there's a little spot here where it can push this to the right. Okay, that pitch mechanism. Now the other spot is then it goes into the speed governor, essentially the prop governor, and that is controlling it coming out, and now it's called control pressure. And that control pressure can flow through all the different control items and ultimately comes down to our control piston, and it would push it to the left. Okay? And when we push that left or right, it's engaged in threads here. It's going to cause the oil transfer tube to rotate one direction or the other in relation to the propeller. It's actually spinning with the propeller, but then, it's spinning at the same speed, but then if you can rotate it one way and it goes into the propeller, because it's gonna, when we put the propeller up here, it'll screw into the propeller or out of the propeller to open and close ports in order to control oil direction. So it's divided into these two paths, and what they do is the supply pressure here provides that pitch increase and provides servo actuation pressure. So it's gonna try to move, it's gonna want to move this piston to the right. It's also gonna get ported through the center of the transfer tube where it goes out, and over here would be the propeller, would be the servo mechanism inside the propeller. The control pressure is used to send the decreased pitch signal. By pushing this piston down here at the bottom to the left, that sends a decreased pitch signal. By screwing the transfer tube, in this case, it would be clockwise when you're facing forward. Okay? So that's used to do that. The speed governor, which in this case is hydromechanical, newer aircraft, it would often be a purely electronic device. Okay? But that's where now we can start to move into newer generations. But in this case, it is still a hydromechanical. That's going to provide prop speed control through the condition lever when we're in the alpha range, above 80% prop RPM. And it does that by controlling how much pressure is being ported down on the control side, down to that piston here, that threaded piston. You can see, though, along its path, it's going to get potentially acted on by several other components inside the PCU. So those are the least selector valve and the overspeed governor. The overspeed governor is another hydromechanical device. It has the flyweights in it, underspeed, overspeed, that kind of thing, right? But that can't take control unless the least selector valve opens to allow it to take control. And that you can see that least selector valve, it actually can see what the supply pressure is. The supply pressure comes from the mechanical pump, goes through the overspeed governor, and it's providing a signal to the least selector valve. At the same time, that least selector valve, if that pressure here drops, it can bleed off the overspeed, or it can bleed off the control pressure. And if it's overspeeding, then the overspeed governor is going to dump that back to the return. Okay, so that can kind of take control. The next one's the reversing valve down here. Okay, reversing valve. What's reverse? If we want to make the prop reverse, which way do we go? Do we increase the pitch or decrease the pitch to get to the reverse range? Decrease the pitch. So what that can do, the reversing valve can pump a ton of pressure into the pitch decrease side to push that sleeve to the left, that threaded sleeve to the left. Say, threaded piston to the left. And that can push it into the reversing range, past fine pitch, past zero pitch into reverse. And then we've got a beta valve at the bottom that's controlled by the power lever. And we'll talk about how that can control that controls our RPM and our prop pitch when it's below 80% RPM, so in the beta range, controlling the propeller blade angle. And then finally, our two feathering valves, our mechanical feathering valve and our solenoid feathering valve, which cause the blades to feather. So how do each of these work? So the supply pressure is kept constant. You can see there really isn't anything acting on it here. The only thing it goes through initially is the speed governor. Once it's through the speed governor, it's called control pressure instead of supply pressure. So its supply pressure, there's nothing really acting on it as it goes down to our piston as well as it goes down to the transfer tube to head out to the propeller. So we always have that full mechanical pump pressure between 600 and 800 psi available to go to the propeller to provide actuation. The control pressure we vary though, and all these different devices we looked at, what makes up the PCU, are going to vary that control pressure in order to move that pitch change sleeve, or pitch change piston, they call it, left or right. And what ends up happening is you get a ratio between those two pressures, right? One's constant, one's higher, one's lower, you're going to get a ratio between them. And so if we have a supply pressure that's higher than the control pressure, so supplier here is higher than control, that's going to push the piston to the right, and it's going to command the propeller to increase pitch. Look at how that works in a minute. If our control pressure is greater, the control being the black with the two white bars, if the control pressure gets greater, that's going to push this piston to the left, and it's going to cause a pitch decrease. It's going to command a pitch decrease. If they're equal, whenever they're equal, this control piston is not going to move. So when it's not moving, it's not going to cause us to rotate. It's kind of a backwards screw setup if you look at it. Right? Usually you twist the threads into like a, you can almost think of this piston as like a big nut. Well, if you put enough force on a nut, you can cause the thing that's screwed inside of it to spin as well. And that's what this thing's doing right here. Now, what's helping it is the whole thing's spinning, and so it gets it to spin pretty easily in there. Okay? When we rig these, when we set one of these up on the ground, we mount the propeller, and then we slide this tube in from the front, and then we actually have to screw it into this device. And how far you screw it in or out sets the rig of the propeller. You put the blades at a certain angle, and then you screw it into a certain point, and if you screw it in properly with the blades at the right angle, you've set your neutral point. So if they're equal, if the supply and the control pressure aren't trying to push the pitch change sleeve left or right, then we're not going to get any kind of a pitch change at the propeller. It's going to, we'll look at how it's going to basically close off the ports that allow oil in and out of the pitch increase and pitch decrease chambers inside the dome, inside the servo mechanism. So the speed governor in the alpha range acts just like what we would see with a typical prop governor, propeller governor. So if we're in an underspeed condition, it's going to increase the control pressure. That's going to send extra pressure here. It's going to go to the pitch increase. The propeller pitch increases, and that's, as the pitch increases, it's going to cause the RPMs to drop, to reduce, right? Until it gets back to that on-speed condition, at which point the pressures will equal out. It will stop it will stop screwing that beta tube in or out, and it will stop it from moving, and it'll block off the ports in the prop. In an overspeed condition, so overspeed, flyweights are out, that is going to cause the control pressure to drop, which means now the supply pressure can push the threaded piston to the right. That's going to cause a pitch increase, and that's going to decrease the RPM. It's going to put more resistance on there and decrease the RPM. Okay? And when it's on speed, by keeping those equal, as I've said, it's not going to try to push that threaded sleeve, that threaded piston sleeve left or right, and the prop will stay in whatever position it was last commanded to. Again, because there's very little force trying to push it one way or the other. And it's hydraulically locked. The oil in front on each side of that piston, when we close off the ports, it can't move because the oil can't go in or out, and it creates a hydraulic lock mechanism. Okay. The least selector valve and overspeed valve, they work together. So what essentially happens is the overspeed governor can't take control. One of the things that's going to happen that will lead to an overspeed is that you have to have a high control pressure in relation to your supply pressure. So the only way that will come into play is that least selector valve will not even allow the overspeed governor to come into play until there is a higher pressure on the control side than there is on the supply side. Okay. Once that happens, then it allows oil pressure to basically travel both ways. You can see here, it allows for drainage during an overspeed condition. It allows for supply during, it's one of the supply mechanisms during normal flight condition. Okay. And if there is a true overspeed condition, then it will port the pressure, it'll port that supply pressure from the overspeed governor, and it will help drop the pressure in the control side, which will cause a pitch increase. So prop pitch will increase, and that will cause the propeller RPM to drop, hence getting out of that overspeed condition. Okay. The next block down here, our reversing valve I mentioned, is going to increase the control pressure, the amount of pressure going down to the bottom here, ultimately, to a point where it can drive the propeller to a very fine 0 and then negative blade angle in order to go into reverse. And you can see that one's directly controlled by the power lever. So it will only activate when the power lever is pulled back behind the ground idle position. The levers work the same way. They've got the power lever has a ground idle position, and then a flight idle position, and a flight max power position all the way forward. And then if you're back at ground idle, you have to pick up a trigger or lift up to bring it back in reversing range, at which point it'll start to actuate this reversing valve. And the further you pull it back, the more pressure it ports, the more pitch decrease, and the greater the pitch decrease, the greater the negative blade angle, which will be more reverse thrust. Now that will, just like in our other turboprops we've looked at, as that blade angle goes negative, as it goes more and more negative, that's going to put more load on the engine. Where is that power going to come from? What's going to happen? That additional load on the engine is going to do what? even in a free power turbine, that additional load is going to restrict the flow of exhaust gas through the turbine. It's going to take more power for that exhaust gas to move its way through the free power turbine, which means it's also going to slow down the gas generator turbines. Now the fuel control is going to get into an underspeed condition, and it's going to ramp up as we go a bigger negative blade angle, more and more negative. That extra resistance causing the core of the engine to slow down is going to put the fuel control in an underspeed. It's going to ramp up the fuel going in to deliver more power to bring the speed back up again. The core speed will come back up. The gas generator speed will come back up. More exhaust gas will be available to spin the power turbine, and that will cause the propeller to speed back up. And the further we pull back on that power lever, the more the blades go to reverse, the more power the engine's going to deliver to try to keep those blades spinning and not slow down. The bottom here then, the beta valve, also controlled by the power lever. So anytime we're below that 80%, our propeller, as far as the speed governor is concerned, what's going on with the propeller when we're in beta mode? What does it think the propeller is doing in beta mode? Anytime this propeller is in beta mode, what's the speed governor going to try to do? It's going to try to go to, it'll be in an underspeed condition. It's going to try to send oil. So it's going to be dumping oil in here to try to go to a pitch decrease, right? To speed that propeller up. And so what the beta valve can do now is we're the propeller's underspeed. Speed governor is going to try to bring the pit to low pitch. But if in beta mode we don't want it to go to a low pitch, if we want to increase the pitch, the beta valve can bleed off pressure in this line right here. That will cause the threaded piston to move to the right, and that will cause a pitch increase. That pitch increase will put more load on the engine, try to slow the engine down. The fuel governor for the engine will try to speed it back up and put more power in it. So as we push forward, it actually cuts off some of the flow here, or it bypasses, instead of the flow going down here, it dumps the flow. These are return symbols. This goes back to the return. Here's your drain that drains it back to the gearbox. So it will port, rather than porting oil down to the control mechanism, we'll port it back to the gearbox. And it will increase the pitch when we push forward on that power lever in beta range. Okay? Once we get into alpha range, this thing gets locked out. It stays closed. It doesn't port oil back at all, and it allows the speed governor now to control blade angle. Okay, when we're in alpha mode. And then the mechanical feathering valve and the feathering solenoid valve. The mechanical feathering valve is manual, and essentially it's our condition lever. When we move our condition lever into fuel cutoff, or sorry, into the feather position before we go to fuel cutoff, it has a feather position. That opens this feathering valve, which allows any pressure that's in the pitch decrease side here, that's in the control pressure, instead of going to the piston, it gets ported here and back into the gearbox. It dumps any pressure that's in this line right here. And so now the threaded piston goes to the pitch increase position. It just gets slammed fully to the increase position. And that means that the blades are going to increase pitch until they hit the stops, which is the feathered position. This feathering solenoid valve works the same way, except this one is automatically controlled. And so this one you can see the auto feather system. So in flight, this is a twin engine. We want to auto feather if we have an engine failure. The electric feathering system, there's actually a switch. If you need to feather it, you flip the switch, it turns on, it opens this valve, it turns on that feathering pump. Goes out, but we don't want any pressure building on this side, okay? It also actuates it does some stuff with the flight low pitch secondary backstop. We don't want it to, we want to limit how low of a pitch it can go if it's going the low direction for some reason. And again, the fire extinguishing system handle, right? That handle opens this and turns this pump on, right? We got to turn the pump on so we have some oil pressure to get it to the feathering pump, the auxiliary feathering pump. We got to get it to feather, and then we've got to open the valve to allow it to go to feather. Okay, so they do the same thing, just one's mechanical, manual from the condition lever, the other one has several automatic things that can cause it to happen. So how does the pitch change system function? It's going to basically, with any of these modes, so anything going on up here, we either are going to increase or we're going to decrease our propeller pitch. Okay? So I'm not going to look at it from a point of how is pitch increased or decreased in alpha, how is pitch increased or decreased in beta, how is pitch increased or decreased in reverse, because it's all the same. If we need to move the blades to a higher pitch, it's going to do one thing. If we need to move the blades to a lower pitch, it's going to do a different thing. All of that, whether they go higher or lower now, is controlled in the PCU rather than in like a beta tube sleeve or a beta ring and actuator system like we had on our first two control system examples, the PT6 and the TP331. So what happens? So if we want a pitch decrease, if our PCU says, hey, the propeller needs to spin faster, right? We're in an underspeed condition. Or we want to decrease it to 0 and ultimately into reverse. What it's going to do, the control pressure, it's going to choke back our supply pressure. Remember, control pressure is always, it's going to increase control pressure. Our supply pressure is always the same. Okay, supply pressure is constant. Right? Supply pressure comes from the pump, goes right down to the tube. Control pressure is what we're controlling with all these different devices inside the PCU. So it's going to increase the control pressure higher than the supply pressure. That's going to push the PCU piston, which is threaded to the left. That force to the left, when it's acting on these threads here, is going to cause the transfer tube to rotate in the direction where it is going to thread out of, this is essentially a nut right here that it can thread in and out of inside the propeller. Okay? That forms the back of the pitch decrease chamber. There's basically a nut right there. So the transfer tube is going to thread aft or to the right in this diagram out of the propeller hub. And so now that supply pressure will transmit down the center of the tube, and it will be able to enter. It's going to open a little port right here. And what's moving, there's these little, the piece that's moving, when the tube moves, this right here, this essentially is a spool valve up here, is part of the end of the transfer tube. And so we've moved this to the right. And that allows the oil in the center to port up and into the pitch decrease chamber. And that's going to push the servo piston to the left. Now, there's also oil at this point in front of the servo piston in the dome. That's our pitch increase chamber. We have to let that oil out. And so what happens is when this valve moves to the left, it opens this, and now it transfers, and there's a section of the transfer tube here that's blocked off. There's a little wall right here. It transfers back. It goes to the back of the hub, back here where the threaded area is. And then you can see this and this are connected. It's a donut. It goes through this little port, and it actually goes back through the propeller shaft outside the beta tube, or outside the transfer tube, back into the gearbox. So the transfer tube allows oil to go out to the prop. The prop shaft, here's our flange and where it mounts in the hub, allows oil to travel back to the engine outside of the transfer tube. Okay. And so that drain path is open, allows the oil to decrease. And so this piston now is going to move to the left, it's going to move forward, and it's going to decrease the blade pitch to the point where it can go to fine or even to reverse. Okay? Once it gets to its point, once this moves, as this moves, what will happen is it'll move back, it'll move, and as it moves, it will cause because this piece right here is stationary. As it moves, it will move this into a position where as it moves, it drags the transfer tube with it until the transfer tube blocks off these two ports here. This whole thing moves, this moves, it pulls the transfer tube with it, and it blocks these two ports off again. And it locks it into that new position. And when it does that too, as it's pulling the transfer tube to the left, that is what's providing the signal back here. That's what's shutting off flow here, okay? Not providing a signal there, but shutting off flow there. The opposite of that, this is our last slide, I promise I'll go quick, kind of happens the opposite direction. So here we have pitch increase. So now the control pressure, remember, is constant. No matter which way we're going, control pressure stays the same. The devices inside the PCU, whether it's the propeller control, whether it's the reversing mechanism, whether it's the feathering valve, whatever it might be, that's going to release the supply pressure. It's going to dump it back to the return. So the PCU piston now, the supply pressure is going to push the PCU piston to the right. That's going to spin the transfer tube the opposite direction, okay, from what we looked at before. Causes it to thread left now, which causes it to thread forward. And now what we've done is swapped upwards. So that oil pressure now can come up, and it comes out here. This is the little block off thing. Remember, this was over here before. Now it's here. So that oil coming down the center now is going to get ported up to the pitch increase chamber that's in front of the piston. And at the same time, when that comes forward, here's our pitch decrease chamber right here. It's very small now. Oil is going to be able to drain past here, back into this kind of cavity, and then through here and back through the outside the transfer tube, inside the propeller drive shaft, and work its way back into the sump. Okay? And so now the pitch is going to increase. And the pitch can increase, if we can start in reverse or fine pitch or whatever, pitch is going to increase, and it can increase all the way to the point where it can feather. Now there is a physical stop that it can hit when this can't travel any further. That's the feather stop. It'll come all the way back until it contacts right here. We're basically at the feather stop right now. Okay. And so that will cause this, it will push on this piston, and as it pushes on the piston, that's going to drag the beta tube back. And if we didn't go all the way to feather, it would drag it back to, at whatever point we've selected, these two wider parts of the spool valve will close off those ports again. And it'll hydraulically lock the blades in whatever position we've done. The only time it doesn't close those off is the position we're in right now, which is where we're going to full feather. And so now there's any oil pressure that's in here is going to keep trying to push it. Now it's at feather, it physically is stopped, but that's how it kind of locks it into feather. And that's the position it'll be during shutdown. That's the position it would be during an emergency shutdown, an emergency feather if you had an engine loss, or any of those other cases where the control pressure is released in order to allow that prop to go to a feather type position. Okay. That is our last prop control device.